great turnout for will be an excellent lecture on the challenge of causal inference. We usually don't have capacity crowds for those topics, but this is a testament to the presentation we're going to have today. So just, so if you don't know me, I'm Craig Boucher. I'm the director of the A.J. Drexel Autism Institute. A little bit about the idea behind this lecture. We have another sort of signature lecture that we do in the springtime in March called the Annual Autism and Public Health Lecture. And if some of you, I look around and see some of you have been to that lecture, we try to talk about a timely scientific topic related to public health challenges in autism. And we task our speakers, and I see two previous speakers who've given those lectures in the room today, with the challenge of sort of talking about a cutting-edge science topic, but also making it accessible for a broader community. And we're close to getting 200 folks per year coming to those lectures from a variety of different constituencies, from researchers to parents to service providers, and it's a great broad reach talk. But what we wanted to do is we wanted to initiate another lecture that would just be a little bit geekier, a little bit more focused on a scientific challenge very close to the work that we do at the Autism Institute, which, as you all know, is about taking a public health science approach to the challenges of autism. So what we're going to do with this fall lecture that we've called the Director's Lecture is we're going to invite a speaker who's doing cutting-edge work with a little bit of a methodological lean, who's doing something new and innovative or thinking about something challenging related to either the Modifiable Risk Factors Program, the Early Detection and Intervention Program, or the Life Course Outcomes Program. And for this first lecture, this comes out of the topics of interest to us in the Modifiable Risk Factors Program. So with that preamble, I'll introduce today's speaker, and we're delighted to have my friend Mark Weisskopf join us from Boston, where Mark is the Cecil K. and Philip Drinker Professor of Environmental Epidemiology and Physiology in the Harvard T.H. Chan School of Public Health. Mark's background, he holds a PhD in neuroscience from the University of California, San Francisco, and also an SCD in epidemiology from the Harvard School of Public Health. Mark transitioned from a focus on neuroscience to a focus on public health issues related to neurodevelopmental and neurodegenerative diseases earlier in his career after he completed an Epidemiologic Intelligence Service assignment through the CDC. So he did that for 2 years working with the Wisconsin State Health Department. He still, amazingly, keeps a hand in neuroscience, a hand in epidemiology. His neuroscience work focuses on molecular and cellular aspects of neural signaling and plasticity. In the environmental sphere, where we know him from, he's particularly interested in the influence of environmental exposures on brain development throughout the lifespan. So what also makes Mark unusual is he thinks about both neurodevelopmental conditions and, as mentioned before, also neurodegenerative conditions. So he works in autism and ALS, Parkinson's, related neuropsychiatric conditions, et cetera, et cetera. So he thinks about how toxins affect brain development biologically, and he also thinks about some of the challenges we have in doing observational epidemiology studies on the influence of environmental exposure on brain health. And today he's going to talk about one of those challenges that we face. So without further ado, Mark.
Thank you. Am I supposed to wear this, actually?
I don't know. So do we need that for the audio?
Do I put that on? Don't have to. Okay, great. Thank you, Craig. That was I don't know, hard to listen to all of that stuff. But thank you very much. And if part of your aim here was to do something slightly more geeky, you got the right guy, because I geek out on this kind of bias stuff. So I hope you could bear with me as I take you through some of the bias issues, because I now see bias everywhere and how we handle that in epidemiology. And so as a first apology, right, so some of this is all driven from my work in autism, but it's going to wind up not quite in autism and a slightly different outcome, but you'll see why I went there, because I think it affects what we're trying to do in our studies of autism, at least epidemiologically. So now I don't have to do this, I'm sure, in this group, so I kept my autism intro slides really to a minimum, because I'm sure you guys all know this long history, and I only put this one up because I think I pilfered it from Craig a long time ago about the timeline of autism from its recognition to the days of psychogenic risk factors to the genetic studies and period of trying to look for the genetics of autism. But what I added, because we can always improve on the shoulders of giants, that Craig, I got this slide from him, is that we may now be in the environmental era with rigorous environmental epidemiology studies of the influences on autism led by people like this guy here. And I found lots of potential photos to pick, but I picked that one. So Craig is obviously at the forefront of this stuff. But I do think that we're in a new era of really generating, and while Craig is one of the many, there are several people now looking at environmental risk factors for autism in stronger studies than had been done before. So it's sort of an exciting period. I'll talk to you today about air pollution work, and this is one of the areas where probably more work has been done than with other toxicants in terms of the relation with autism. And this is a woefully inadequate slide for all of the work that's out there. Heather Volk here in the audience is one of the prime movers in air pollution studies in autism. I do have her studies, at least one or two of her studies there. So, but just to let you know, as a background, since we will be talking about air pollution, that first of all, it's many different things, right? There's bad stuff in the air, so there's issues of, we're just talking about the kind of global dust that's out there that we refer to as particulate matter, that's whatever that may be made up of. It has constituents to that. You can break it down further to metals in the air. There are also gaseous pollutants. There's pollutants that come from traffic, from other sources, things of that sort. So it's a very heterogeneous exposure, and many of the studies look at things. In terms of air pollution, autism. From my personal feeling is that there is sort of the overwhelming majority of these studies seem to show some association with autism. There are slight differences when you look across the studies based on exactly how they were done, exactly what they're looking at. But there is certainly a sort of core of a signal there that many of us are trying to tease out and see what's actually going on. One of those aspects of air pollution that has received a fair amount of focus is traffic-related pollution. Heather, some of her papers have to do with how close you are to a freeway, and therefore as a measure of traffic-related pollution, things of that sort. Of interest, though, and I'm summarizing a lot of work, that while the majority of studies do seem to suggest some association between higher exposures around the perinatal period to air pollution and higher risk of having a child with autism, not all do. There are these ones in red here. Gong et al. Are a couple of studies out of Sweden, and the Gushin study is kind of a conglomerate of European cohorts that also did not really see a signal. And that's of note for several reasons. One is the vast majority of this work on air pollution and autism has been done in the United States. Those are two of the maybe 4 studies that had been done outside of the United States. And so there are questions of, well, are things different outside the US and inside the US? The other issues here is that Sweden happens to be pretty clean as far as traffic pollution goes. So it's you're at a much different place on the dose response curve. So that was another issue. At least one of those Gong papers and the Gushin's papers actually used a scale or kinds of scales to either classify people as autistic or not, or just use the scale as a continuous measure. So there's some issues of, is there a difference if you're using a continuous scale like that? So with that said, I had started in this using the Nurses' Health Study, which is based out of Harvard, 100,000 nurses across the United States, but thought, well, let's see if, could we go to another place in the world where maybe exposures are higher, where conditions are different. There were these studies out of Europe suggesting things might be different there, so we wanted to sort of branch out more from the United States. And also try and get at other aspects of this, like critical windows of exposure. When does exposure really matter? And to really do that, we had suggestions of that from our nurses' work, but the nurses' work was dealing with a few hundred cases of children with autism spectrum disorders, and we wanted to try and grow that up to much larger numbers where we could really dig down in more depth as to this question of when exposures matter. So with that, I, through other collaborations, managed to set up something in Israel where we started to look at this question, in part because they have sort of pseudo-national health care, and they have national benefit, which we'll get into for autism. But it provided a great setting to potentially get at some of these questions that we wanted to explore outside of the US. At what you'll see for NO2, for traffic-related pollutants, it's actually not necessarily a higher exposure setting than many places in the US, like Boston. But for some exposures, like particulate matter, the general dust, it can get quite high. So it offers opportunities to look at a different range of that dose-response curve. So to do this work in Israel, we collaborated with folks at the National Institute of Insurance, which has this national benefit for any family who has a child with autism. And it's central for the whole country, so we could use countrywide data. We wound up focusing on the Tel Aviv area because of our exposure models, which I will get into. But that Tel Aviv Central District area, this is the Mediterranean here. And this is Tel Aviv, north up in Netanya, and south down in Ashdod. And that actually captures close to half of the Israeli population that's there. And the population then we looked at was born 2005, 2009. They all had to be alive and still living in Israel at age 4. They have to have Israeli mother and father, partly so we could track things. And then, as I say, the autism is identified from this National Insurance Institute. And the only thing I will say about that is that it's a benefit, it's a financial benefit given to families who have a child with autism spectrum disorders. And it is totally independent of severity or needed benefits for that child. It is simply, if you show that you have a child with autism spectrum disorders, you get this financial benefit. So there's a very strict process for providing documentation and specialist reports that involve personal interviews and interactions with the kid from the children's doctors to verify that you in fact have, or the child has autism spectrum disorders. But you can fall pretty much anywhere on that spectrum of disorders. And if you've met DSM-4, now DSM-5 criteria based on all the data put forward, you get this benefit. So in theory, we could take the entire population, the rest of the population, and look at the whole thing, but that just gets computationally hard. And in fact, the National Insurance Institute has a dinosaur of a computer that they refused to let me buy them a better one. So we decided to make it computationally less intensive and just randomly sample 20% of the rest of the children born during this period as our non-ASD cases. We collaborated with folks at the Technion in Haifa to get our exposure estimates. So they build models of air pollution across Israel. Nitrogen dioxide is one pollutant that is monitored in Israel, and these green dots here are the different monitors. It's really, so we're looking at NO2, but it's just you have to consider it as a tracer or a marker of traffic pollution. So anything I show you, we can't necessarily say it is the NO2, but we think it's something coming out of tailpipes of cars that's related to traffic. So to develop their models, they take advantage of road networks and traffic patterns. They have these monitors that are sampling every half hour across Israel, so they can get very fine detailed maps across Israel at about a 500 by 500 meter grid of NO2 levels, and we can average over different time periods. And that, because so much of the population here, this is where the monitors are, that's why we focused on this part of the population for this work. So this is an example of what we get out of these air pollution models. Different periods of the year, winter, spring, summer, and fall. Red is generally high, blue is generally low. I put these arrows here because this is not quite fair in that the scales are different on these four, so it's not perfect. But just to give you an idea of how these things spread, it'll depend on wind patterns and things of that sort. But there's a fair amount of fluctuation across the year. This is just looking over several years at the yearly seasonal fluctuations across this area of Israel. So we get a lot of variation in this, and a lot of both temporal and spatial variations. So Tel Aviv is really centered right in the middle of this scale right here. And actually I will say that this mean at about 17 parts per billion of NO2 is almost exactly what we see in Boston. And my guess is it would be probably pretty close to Philadelphia too. So it's not, and this is in large part because it's really driven by traffic, which all these places have, right? But of note, it is about 4 times higher than Sweden, which is what they were looking at in the Gong studies where they didn't see an association. It was also slightly smaller, I believe, in terms of numbers. So For the statistical methods, part of the idea here was to have, because we have much larger numbers than we had in their cell study, we could take more advanced statistical approaches to looking at this. The basic framework is a logistic regression. You're asking what predicts having a child with autism or not. So we can look at splines to see whether there are sort of non-linear strange relationships. There really didn't seem to be any. We can adjust for a whole variety of factors. Very important, and I'll probably mention this a few times, but these sort of epi-methods issues that crop up, there's some very interesting ones about how you go about your exposure assessment, and modeling exposures in this kind of a way off of monitors and things like that offer certain advantages in terms of confounding bias. And one of those are the things that would tend to confound a relationship with that exposure have to be things that sort of predict your model predictions, right? So things like year and month of birth are important for seasonal and long-term trends in air pollution and autism rates. Population groups, so we had done work before in Israel in this same data showing very different prevalence rates of autism in these different groups. There's the general Jewish population in Israel. There's the ultra-Orthodox Jews that are also Jewish but have very, very different daily practices and lifestyles. And then there's the Israeli Arabs that also have somewhat different lifestyle practices and sort of other factors that go along with their lifestyle. But what the problem is that they can vary by where they live. So in that way, that could also be related to exposures just because of the neighborhoods they tend to be in. We did look at paternal age and then socioeconomic status indicators from this national data that we could adjust for. We also have, from the advantage here is that the ministry keeps all sorts of information, so we have information on child sex, gestational age, birth weight, all these other factors that we can also potentially consider, but we have to be a little bit careful in considering these, maybe not so much parents' immigration status and the wages, those are socioeconomic indicators that would be good to know, but the other ones like gestational age and birth weight, we have to worry about them being intermediates, right? So if we think that air pollution or traffic pollution may increase the risk of having a child with autism, it's conceivably, theoretically possible that it could do that if you see it, via having effects on gestational age or birth weight. So you don't want to just willy-nilly adjust for these things because they may be part of the causal path that we're trying to look at. Most importantly is that we now are talking numbers and size of a population where we can start to use more sort of sophisticated, fancy approaches to considering exposures at many, many different time periods. And we're using something called a nonlinear distributed lag model, which effectively allows you to look literally like week by week as an example. These are done in different time frames, but you can essentially include all of them in your model together. And that's very important for another epi-methods issue that I will touch on at one point, which is the need to sort of control for other exposure periods, especially with something like air pollution that we know is correlated over time. So if you're looking at exposure during one time period and you see something, how do you know that's really a causal effect, or it's just that that's associated with exposure 2 months ago or something, and that it was another period that mattered? So we'll get into that a little bit more, but distributed lags, essentially one of the advantages is that they allow you to kind of control and have all of those time periods of exposure in at the same time. These results I'm showing you that I will be showing you are per an interquartile range difference in the NO2 from the 25th percentile to the 75th, which is about 6 ppb of NO2. So very quickly, basic demographics of this group. Most importantly, right now I'm dealing not with a couple hundred or 300 cases of children with autism, but this is only half the population over this time period, and I've got over 2,000 cases of autism. So that really helps in trying to look at more fine detail of these relations. We've got the 20% sample of the controls here, and you see things that we would expect. There's a larger general population percentage. That's just the Israeli demographics. You've got some twin births, siblings with ASD, higher, obviously much higher percentage in the children with autism. Birth weight, nothing terribly different here. Maternal age and paternal age are slightly higher, as we might expect in the children with autism. And this is a poverty index score that they use based on a whole variety of factors. And this is certainly of interest, and we're looking into this a little bit more about how the children with autism seem to have a slightly higher poverty index, meaning actually now I'm wondering whether that, I'm forgetting now whether up is, this is unadjusted, so I'm not sure whether that is actually higher or lower, but anyway, we'll get to that. It is somewhat related to that poverty index. So to cut to the quick about these results that we found, so the very first thing we did is say, well, let's just look, and this is, we had done this before in the nurses, at the pregnancy period, so exposure over those roughly 9 months of pregnancy, and exposure in the same time frame after pregnancy. And so the basic results we found were this. So not dissimilar to what any others have shown, we see a slightly increased odds ratio for autism among women who have a higher NO2 exposure. This is per interquartile range. It's only 10% or so higher. And we see it in both periods. The issue is these are models where I've modeled each exposure period separately, right? So this is one model, and this is an entirely separate model. And what I've told you is that air pollution is correlated over time. So your exposure in 9 months and your exposure in the next 9 months are somewhat correlated. So even if we think for a moment that maybe this is causal, how do we know which period is the important one? These are the exact same results. I'm just putting them on a different scale. And I'm going to show you why I'm putting them on that different scale. So obviously the scale has now shrunk those confidence intervals. I'm putting them on this scale. This is still the separate models because the fact that they are highly correlated means that if you put them in a model together, you're gonna, you lose power effectively, right? It's hard to distinguish the effects of two things that are very correlated with each other. So when you do that and you throw them in the model together, you kind of expect that confidence intervals are gonna increase and get larger because you have less ability to sort of distinguish between the two of them. And that is exactly what we see when we put them in the model together. But the other thing that we see that was striking is the results sort of change now. So now it actually looks like during the pregnancy period, we're seeing protection, right? So higher NO2, higher traffic exposure of where the mother lives, less chance of having a child with autism. Whereas in the 9 months after, we actually see a higher risk of this, right? So the first thing I want to say just for the epi-methods point of view, and Enrique Schisterman has a great paper in Epidemiology on this in 2017, is that you should not be afraid of putting correlated variables in a model together. That is what regression analysis was designed to do. So it is okay to do, and you just have to know what the effects will be, one of which will be to balloon these confidence intervals, right? But if you truly think that these things are correlated for some other reason, and you want to assess their independent effects, you have to do it if you want to avoid bias. So what I'm saying is that likely one of these is biased, right? Because I'm not accounting for the other period. This, if I have my ideas of how these data relate, I think is going to be less biased. We can get into a discussion about this. But that's one issue. The more striking one is what's going on here, right? So that was a thing that caught our attention. I had conversations late at night on vacation with Heather about, what do you do about these kinds of findings that are a little bit weird? So we, put a lot of thought into this. But before I go into that, I will say that we did some other things, and a very important thing I want to give, because both of these are actually technically significant, right, at the 0.05 level of significance. But importantly, when we also included the 9 months prior to the pregnancy, so before conception, we don't see any association, at least not a significant one. Whereas the associations with those other periods didn't seem to change. Yeah?
A quick question. When you're talking about the 9-month pre-pregnancy, are you just taking a cumulative exposure measure?
We're just averaging. So those monitors that, those models predict almost on a half-hour basis. So we're just averaging over the entire 9-month period for that. And so if we didn't do this as the main analysis because of our time span. When you need to consider exposures 9 months before, you wind up cutting off a lot of your people because you've got to give them those extra 9 months. But when you do that, you basically don't change those results I showed you before for the pregnancy and the post-pregnancy, but you don't see anything for that pre-pregnancy period, which is important and we'll come back to. In addition, we have all this other data, different sensitivity analyses, additional adjustments for other things, restricted to gestation weeks 38 to 41, excluding those that have siblings with autism under the assumption that that may be a more genetically driven form, or adjusting for gestational age and birth weight, in fact, didn't really change these results much at all. So they seem to be pretty robust. And the next slide, although it's not the main point of my talk, I do want to put out there because it's something that I've sort of seen subtly before, and it's strongest here, and I want people to know it and think about it, is how this may differ by sex. So we had hints of this in the Nurses' Health Study, but the numbers were so small it was a little hard to tell. Here the numbers are higher, although that said, there still are, because of the distribution of autism between boys and girls, there still are many fewer girls. But it certainly looks like what we're finding is driven by an effect from boys. In girls, it's a little bit more questionable. These are models with both of them in together. So for whatever it's worth, we seem to see this a little bit more predominantly in the boys. But I'm just showing you these 9 months averages when I spent all the intro sort of talking about how great it was to have 2,000 children with autism because we could do all this detailed work. So we did do all the detailed work, and we did a distributed lag model based on time since conception for these folks. And this is what we see, right? So these models, by their nature, distributed lags, are effectively accounting for every week. These are weeks of pregnancy from conception here to roughly birth, because as Heather and I were just speaking about, this is slightly problematic since not all these kids are born at 38 weeks. So this gets a little bit fuzzy right in here, and it's something we need to work out more. But the bottom line is, when you essentially account for every week of exposure to these people, to the mothers, families, we again see what looks like this sort of protective effect at around week 13 or so. And yet, when you come out here after birth, now there's something that actually looks significantly like a risk factor. So, very interesting, very odd, sat with it for a long time. And just because it's the way I think, my immediate reaction to this was some kind of bias going on. I was not about to go out and tell mothers in the 13th week of pregnancy to start sucking on a tailpipe of a car. I think that's probably not a good thing to do. But how do we figure this out? How do we know what's really going on? So before getting into what we went in to do, clearly there are limitations and strengths to what we're doing. We're using modeled exposures at the mother's address at birth. Absolutely, that has measurement error related to her individual exposure. That is a whole other track of Epimethods, interesting issues that I can get into later if anybody wants, but I probably won't do as part of the main talk because I want to talk about something else. I will say that when you have error like that in assigning the actual personal exposure from some kind of model, when the mother is obviously not sitting at her doorstep for the 9 months of pregnancy, you know, if you probably reasonably assume that's relatively random, and we can talk about that, that would be likely probably to bias effect estimates towards the null. So this is very common in air pollution epidemiology. You get these very small effect sizes for ambient measures of pollution, and certainly a healthy part of that is that you've got a lot of measurement error, and so you're driving results towards the null. But as I will talk to you later, I don't want to say it's all bad, because actually using models like this has some benefits from a confounding bias perspective. That again, I can get into more if you want. We don't have detailed, yeah, sorry.
Just a quick question before we move on to the next point. For the home address, what's the distribution for employment for the moms in this study? Right,
so that's another source of error in that we don't know that, right? So we don't know where they work, and clearly they are moving around to where they go. It's a very interesting issue. I have a whole set of backup slides that I could talk to you about what I think happens and what's going on with that, and we can talk about it later. But for the simple point now is that's contributing to some of the error, right? Because the mother goes off to work somewhere, does something during the day, is getting a different exposure profile than what she has at her home, and so we're not getting the measurement exactly right. So we don't have detailed autism spectrum phenotype of these kids, and that is a big problem when you're dealing with big data like this, because it's just hard to have that on so many people, and we're using, to some degree, administrative data sets. I think it's a big, really interesting, and I think the more we can strive to try to phenotypically identify different components of this, it could be really interesting and worth doing. Can't do it in this data set, so that's a drawback. What we gain instead of that is a population-based thing. We're looking at all of Israel. It's very large, so over 2,000 cases. The autism spectrum thing is independent of services, so we're not talking severity of autism issues here. And the large number allows us to do this negative control exposure approach, which I realize is the first time I've said this, but the idea of looking at different exposures where the sort of confounding structure is the same. If you find an exposure that is not related to your outcome, it has important implications of what types of confounding cannot be going on. So I'm going to leave it at that for the moment, but I'm happy to talk to people more about negative control exposures. But that is, I think it is hugely important, and that's why I wanted to do this DLM or have multiple exposure periods in at the same time, because I think it, from an epi-methods causal inference perspective, it gives you huge advantages. All right, so overall, we see no association with the pre-pregnancy period. So that actually serves as a negative control exposure because the sort of drivers of pollution before pregnancy, during pregnancy, and after are very similar, at least the time invariant ones. So the point is there, it rules out time invariant factors as potential confounders. Things like, for example, socioeconomic status, right? It argues against that being responsible for any association. Critical windows of exposure, as I've been now harping on, you really need to include different exposure windows together, because if they're correlated, let's just say for the moment this is causing an increased risk of autism, then this will look like it is too, even if it really isn't, simply because it's correlated with this. So to avoid that, you have to put the two of them in together. We have this scenario now where we see these opposing effects. So that leads to these really interesting problems, which is that if you're not accounting for these exposure windows in detail, you could get the wrong answer for a window, like one of these might be wrong. You could also potentially, if you averaged over all of this, you could potentially see nothing because you're kind of balancing out positive and negative associations that then come to a null one overall. So if things are going in different directions, now you have to be very careful what your window is so you're not losing effects that might really be there. And I will say that some of these prior studies of traffic pollution, this could be an issue, that maybe the ones that didn't see anything, maybe they weren't accounting for these other time periods in the right way and sort of washing out an effect or seeing biased effects because of correlations with other time periods. But that still leaves that, like what is going on? This is sort of my summary slide about the various epidemiological methods, and this is where I geek out, and this stuff has sort of led me down all these paths about different epi methods and causal inference issues related to it. The first two here I'm not going to talk more about, but I'm happy to talk with others later about if you want. One is that negative control exposure issues and what advantages they can bring to a study. They were first described for epidemiology by Mark Lipsitch, and then I and some others too have written some papers on the topic and how they get used and what the assumptions are under them. The other issue is this one of using a more proxy measure versus more personal measure. There's I don't want to get totally in trouble, but there's a big move towards exposome, getting super personal, measuring everything in the blood, and there's huge advantages in that, and we absolutely want to do that. But I want to make an important pitch to not forget about some of the advantages you get when you don't have a personal measure. And that's what I was talking to you about when you're using something like a model of exposure. And again, I can talk to you more about this paper, Tom Webster and I sort of described the issue. You can avoid a lot of personal behavior confounding bias by using modeled estimates. So the question in the back about where are these women working, where do they go during the day, absolutely contributing to error in our estimation from the model of what they're exposed to. But if they are, their patterns of where they go for work or what they do during the day away from their home is driven by personal behavior characteristics that are really hard to capture. If those things are removed, if they, for whatever reason, some of that aspect was also related in some strange way to risk of their child having autism, we would have to try and account for that if we're using a personal exposure measure. We don't really have to account for it if you're using a model. Now, there are some issues around that, but that's sort of the main point, and we can discuss it more if you want to read that paper, or if you have other questions, I'm happy to talk to you more about it. But I wanted to skip over those two largely because what I want to talk to you today is how do we deal with this? What is going on here? What do we think is really happening, right? Is this a true protection, that somehow there's something about traffic in early pregnancy that is good for you? Or are biases potentially creeping in here in some way? And since I see biases everywhere, I think that may be what's going on. Now, the issue is that there are actually, one, this is very well described, another one that's sort of somewhat described, biases that I think can very easily create the kind of scenario we're seeing here. This is one, and I apologize for the lingo, but conditioning on a collider is, I don't know how many of you have done sort of directed acyclic graphs or DAGs and how you graph out relations between things, but conditioning on a collider is sort of the DAG terminology for selection bias. So many of you, if you don't know DAGs, you think about selection bias, and it basically comes about because you're selecting a certain group into the sample that you analyze, selecting them out of the larger population you sort of thought you were going after or trying to make inference to, right? So one of these biases is when you have a scenario like this, where maybe nitrogen dioxide or some aspect of traffic pollution is related to pregnancy loss. And the reason for that is to do an analysis of a prenatal exposure and the risk of autism, you are, by definition, conditioning on the child being born. Because if the child is not born, we have no idea whether it had autism or not, right? So that is a sort of subtle, sneaky way that bias can get introduced because we are conditioning on this. If you've had pregnancy loss, you're not in my study. I cannot do the analysis. So now the problem comes is that if nitrogen dioxide affects pregnancy loss, and there's some other factors, genetic susceptibility, internal stress, whatever factor you want to throw in, your pet factor, that also affects pregnancy loss and affects the risk of having autism. By conditioning on pregnancy loss here, which in DAG terminology is called a collider because both NO2 and this unknown U variable affect it, you create an association between the U and the NO2 that is not there in reality in the population you're making inference to, that is effectively all conceptions that happen. I think I have an explanation of this. There's a great paper by Miguel Hernan that sort of describes this type of bias, selection bias. This crops up in many other places. It's the same principle as if you're used to sort of longitudinal studies of cohorts, loss to follow-up. So if you have informative loss to follow-up, this is the structure you have to worry about, and that you may be getting biased estimates from that. Miguel has that paper. So that's a good paper to read on this. Importantly, it actually doesn't matter whether there really is an association between NO2 and your outcome, or whatever that exposure is, or not. Okay, this bias can happen, even if there's no association. If there is one, the bias could still be there, and therefore somehow modulating what you're seeing of the true causal effect of, in this case, NO2 on autism spectrum disorders. This is a very well-known, possibly best known in reproductive epidemiology, as the exact structure underlying the birth weight paradox, which is if you look at the effect of cigarette smoking and you consider birth weight and infant mortality. It was reported in the early days that among low birth weight children, mothers who smoked that was protective for infant mortality. And now, there too, it was like this paradox of thought, why should smoking be protective for infant mortality? Well, it turns out that there's very good reason to believe that this is what's going on. That if you look only at the low birth weight children, you're conditioning on birth weight. And if the smoking changes your risk of being low birth weight, and there are other factors here, you can get these strange protective associations. And the intuition behind this, in the context of NO2 and U, is that if I am, whether this line is here or not doesn't matter. If I am looking at children who are born, because I have to, if nitrogen dioxide or traffic pollution is high, but that nitrogen dioxide leads to pregnancy loss, right? Then it's sort of an odd child that has made it despite having high nitrogen dioxide, right? But if they do have high nitrogen dioxide exposure, they must be much less likely to have this, or their chances of being born would have been much, much lower. So by selecting people who are born, the ones who have high nitrogen dioxide exposures are much less likely to have those other exposures that would have caused pregnancy loss. Because if they had both of those, the chances of pregnancy loss go way up. All right, so that's a lot to get over in 30 seconds. So I'm happy to talk to you more about that if you want. But there is sort of intuition that we can talk about more and think about it. Zayan Yu and colleagues working with the Danish National Birth Cohort also recognized this when they did a study of PFC, polyfluoroalkyl compounds, and ADHD, and seemed to see suggestions of, well, I think there it was more no effect, maybe trending towards a protective effect. And they have a nice paper that sort of describes this issue of live birth bias, that you can get problems because of the fact we have to condition on having a born child. In their case, it was kind of theoretical, so they couldn't really say whether that chemical exposure was affecting pregnancy or loss, and I haven't said that about air pollution yet. But it certainly, they raised this issue that we could have this problem. Same as the smoking paradox, birth weight paradox. And that one is explained well in Sonia Hernandez-Diaz's paper. Yeah.
Are you going to go back to talk about directionality, or was that it? We were talking about the negative association between you and pregnancy loss.
Yes, I am going to go back to direction.
Okay, that'll wait.
Yeah.
Okay, I'll wait then.
Okay. I think. If I don't, stop me.
Okay, yeah.
So what happens with twins? Where pregnancy loss of one twin would also cause pregnancy loss of the other twin? Or increase the risk of pregnancy loss of the other twin or major comorbidity.
So you're saying that in the scenario that you might actually lose the second twin because you lost the first one, or you're saying that one twin is
So
lost?
the loss of one twin
Right.
increases the chance of a loss of another twin. I'm wondering what happens in the context of twin studies where you have early fetal loss from environmental exposures.
Twin studies, you mean when you are studying the twins eventually? Yeah, no, so that is certainly something you would have to think about, is if the key question is the exposure that you're interested in a twin study is related to this selection process. So if the exposure you care about is related to why one of the twins maybe was lost, and therefore the pair is not in your study because they're no longer a twin pair, that could be an issue, but you have to think about whether your exposure contributes to that loss. So this is one way that it can happen, and this is a way where you effectively change the distribution of your exposure of interest and other exposures that matter in the population you analyze, and change in terms of with reference to the larger population you're making inference to, which is sort of all conceptions, right? So that's sort of changing the distribution of exposures. There's another way you can get this without changing the distribution of exposures, but through something that is a form of effect modification. All right. So if we actually have fetuses that tend to be more or less susceptible to the effects of traffic pollution, and let's just dichotomize them for the moment as susceptible or not, right? And your population of conceptions, these are all conceptions that you really want to look at, is some mix of those two, but you don't know the mix, right? You don't know what that issue is, so you can't account for the susceptibles versus the non-susceptibles. Then you're looking at something like this, where maybe we have, these are totally made up numbers, but you've got like 120 susceptibles, 240 non-susceptibles, same over here, and now I'm just going to split them for sake of argument into high exposure to traffic pollution, low exposure to traffic pollution. But the susceptibility here is with reference to the air pollution. Okay, so you've got a group that's susceptible and a group that's not. In the low air pollution, let's just say for sake of argument that you don't lose any because the air pollution is low, so the fact that you're susceptible doesn't matter because you don't have the exposure. So it's like it could be a gene-environment interaction or something. These are guys that are also more susceptible to getting autism. All right, so that's another component of this. So if we look later, and I just made this up, let's say you get these black squares are cases of children with autism spectrum disorders, that there are 3 among these 120 that are the susceptible group, but there's only 1 among the 240 that are non-susceptible. Just throwing hypothetical numbers out there. So the problem comes is that if the susceptibility is also related to air pollution, and you lose a subset of your susceptibles, right, let's say 40, one of which was going to be a case of autism spectrum disorder, but now doesn't make it. You now wind up analyzing this group without knowing that you've lost these guys, right? So now we've got same rates of autism, it's just that we have fewer of the susceptibles. Same rate of autism here, but these guys all made it because they're not susceptible. But now we have an incidence of 2 out of 80 here and 1 out of 240 there. That's identical to the 3 out of 120 here and the 1 out of 240 here. I have not changed the rate of autism in either of these groups. So what that also translates to is that autism is not related to air pollution in this example I'm giving you here. But if you actually do the numbers on the people you can analyze, which are the ones that made it to live birds, our low air pollution group is 4 cases out of and 356 non-cases. Our high air pollution group is 3 cases, 317 non-cases. And if you actually calculate out the odds ratio, you will get a protective one of 0.84. So there's no, this is a complete bias because I've set it up to have no association between air pollution and autism, yet I've got a protective association. And as I said, this is a form of effect modification because you've got different things going on by susceptibility status. And again, you can think of it as if they're susceptible to the effects, more susceptible to the effects of oxidative stress or immune activation and things like that. So this sort of depletion of susceptibles is a second form of bias that can lead to these sort of odd protective associations. We just published this, Ron and Raz et al. in AJE, if you want to look into that further. But an important aspect of both, again, this is still sort of theoretical, I'm giving you kind of epi-causal methods reasons why we might see protection. But an important aspect of both of these is that the exposure, in this case the traffic pollution, has to be related to the pregnancy loss. All right, if it's not, you won't get either of these forms of bias. Okay, so, all right, well, if we want to go further and say, is this really, could this protection be a bias? Is it really happening? Can we look at that? Is that something we can look at? Well, yeah, in theory, we can. And some people have. There's very little literature on this. There is much more on air pollution, different aspects of air pollution during pregnancy, and birth outcomes like birth weight or prematurity. Part of the reason for that is those are very countable and identifiable outcomes. And that is what we do as epidemiologists. We count things. So when you can't count them, we got problems. That said, some pregnancies are lost. And those get documented, and you can do analyses of pollution exposure and those losses. Not very many have been done, although there are some suggestions from that it could increase the risk of loss of a pregnancy. But there are fundamental problems about this. I mean, the few studies that tend to be very small, and some of them are, literally not controlling for anything, and they have small sample sizes, in part because, there aren't very many of these. You're dealing with medical records somewhere. It's only the ones that get actually accounted for in medical records. None have sort of looked at critical windows. But you have this fundamental problem that you can really look at is what gets captured in the medical system, right? So are we missing stuff? This is potentially a very select group. And we, in fact, have evidence that we're missing a heck of a lot. All right, so pregnancy loss, this is a pregnancy loss pyramid, where if you start from the base of conception, you actually wind up only sort of, first of all, of 100 conceptions, some estimate of around 30% of those actually get to a live birth. That is a lot of missing data. Maybe 10% of those losses get captured. These are some estimates, these numbers fluctuate, where maybe you could count these, and that's the studies that are out there. They're sort of looking at some of this stuff. But even that, there's a lot that you're missing. And the more you're missing, the more chance that, maybe you're looking at a select group, maybe they're weird biases of who gets there, and are you really seeing the full picture? Now, that's not to denigrate what has happened, because this is fundamentally a very difficult problem. How do you do a study of something you don't see, right? We count things in epidemiology. You can't count those. That said, so we sort of said, all right, what do we do? And I actually am trying to retrace my thoughts as to how I even got to this place where we decided to go. I'll tell you where we got to, but I'm forgetting the path to get there completely. But we said this is a problem. What are we going to do in our data? And most importantly, we didn't have at the time with that NII, the National Institute data, we didn't have missing. We didn't have identified losses. We just had the autism data and the full birth data. So we were like, how are we going to use that to figure out whether traffic pollution has led to losses? So this is actually a problem that is not unique to epidemiology. Other fields deal with this. This is one of the more famous ones. So physicists who want to study at the quantum level subatomic particles that are fundamentally unobservable to us because they're too small, too short-lived, things of that sort. So they cannot see the actual things that they want to understand. And so they got around it by developing what's known as the bubble chamber, which is they make events happen, events at the subatomic particle level within a sort of cloud chamber that then leaves traces of those particles that they wanted to see. So they can infer all sorts of things about the actual subatomic particles by the effects that they leave in the bubble chamber, in this cloud chamber. So we said, can we do something like that for epidemiology, and in particular for pregnancy loss? So at the risk of getting super geeky and doing something I was definitely told to never do when you give a talk, which is to put equations up, I'm going to put equations up, but don't worry if you don't get them all. I'm trying to keep them simple, but I'm happy to talk to anybody more about them afterwards. So let's think about this for a moment and say, what would we really want to do if we wanted to know that some exposure led to pregnancy loss? So what we really want to do is tackle it in the way we know best, create a cohort of conceptions, follow them forward, and see which ones are lost. Right? That's typical cohort study. Our problem here is we don't know the conceptions, right? We can't identify them all. Half of mothers, or some estimate like that, don't even know they're pregnant, right? So they may even lose the pregnancy before they even realize they're pregnant. However, what we do know, and it's because of the purity of math, right, that total conceptions, let's say in a week, right, can be broken down into those that are subsequently lost and those that result in a live birth. You can talk about exactly how they're lost, all those things, but fundamentally, if you conceive, whether you know it or not, that will either result in losing that conception or a live birth child. Now, the problem is, so this can be written as, total conceptions is equal to the sum of pregnancy losses plus live births, which we can then rewrite and say live births. And the reason I'm rewriting this is the only one of these three things that we know and we see and we can count is the live births. Okay? So we can rewrite this to say live births, which we can count, is equal to total conceptions minus whatever losses happened. And let's just say in a week as a time frame, right? So now the problem is typical administrative data. So this now we're getting somewhere because this we can count. Typical administrative data, though, that's not what you get, right? You get how many births occurred this week. And that's not exactly what we're talking about here. We're talking about how many births came out of all the conceptions that happened in the week. But those births are going to actually be spread out over many weeks because gestational ages will be different, right? So what do we do about that? So this is where we came up with this new metric, and this is made up data here. And the repro epidemiologists, if there are any in the room, will tell me right away that that's a bad description of distribution of gestational ages, but this is fake data, so don't worry about it. We make up this new metric that we're calling live birth identified conceptions, all right? So on the top row here is just daily birth data from somewhere. Pick a hospital in Philly, right? And just count their births every day. We can now take the gestational age estimated, admittedly, there's some error there, with each of those births and resort them into their estimated conception week, okay? So what we now have down on this row is a week-to-week estimated total number of live birth identified conceptions. That is, this is our estimate of the number of conceptions that resulted, the number of conceptions this week that resulted in a live birth at some point later. All right, I've just resorted the data. That's all that we've done. So, more math, apologize. For a given conception week, right, the live birth identified conceptions is equal to, as I said, the total conceptions minus the losses. So some association of some exposure, whatever we want, with this new metric, live birth identified conceptions, if we see something, if there is some causal effect, well, it has to be acting on one of these two, right? There's no other way you're going to change live birth identified conceptions based on how I've defined it. So that's something we can do. This is just a typical model in a regression, right? The expected number of live birth identified conceptions given your exposure in some set of covariates is equal to that. I've just put it in a linear framework. You can do whatever you want with it, but that's a typical epi regression anybody can do. We're still stuck with this issue of, okay, let's say we see something, and X is associated with live birth identified conceptions. Is it because of effects on the conceptions, or is it an effect on the pregnancy losses? So here's where you just have to consider the timing of all of this, and it's a little odd because we've gone back to conception. But if we consider the preconception period, conception, gestation, and birth, right, we might have an exposure 1 that occurs over here. If it does, well, that one could certainly affect the chances of conception because it comes before conception. Exposure 2 here during the gestation period, that's after conceptions. It is, unless we're going to change the time-space continuum, it's not going to affect the conception, right? So if an exposure in this period is related to LBIC, it must be acting through pregnancy losses, with the caveat, of course, that if it's correlated with other stuff, if it's confounded, we have to deal with that. But that's sort of what we do in epi, and any study on air pollution or whatever is going to have to do that kind of a thing.
It could be correlated with exposure 1.
Could be correlated with exposure 1. So in that case, if we thought that was going on, we want to capture exposure 1 and adjust for it. Or we have to account for that. And I'll show you what I think is the predominant problem that we need to worry about and how we deal with it. But yeah, you absolutely have to think of your exposure as you would in any, but still now what I would say, what I'd argue is we're now still in the realm of any typical epi study saying you got to think about your exposure and what are the confounders of that. This is now I'm just getting, this is the real geeky part, right? So that's just what I said. So the causal effect is the expected value of LBIC when X goes up by 1, subtracted by the expected value of LBIC with X. Right? That now we just rewrite, replacing LBIC by TC minus PL. All right? Same equation here. That can just be rewritten as separating out these two as the expected value of the total conceptions when X is +1, minus the expected value of the pregnancy losses when it's +1, minus separating out the two again here. Right? This is just algebra on an expectation level. But the key point here is that I've just told you that if the exposure is here, TC has to be independent of X. So this is equal to this. And so you've got this minus this is 0. So those just cancel right out. And what you're left with a little bit of rearranging of these terms, is when you're looking at LBIC, and whether those change with X, you're looking at the exact equal and opposite effect on pregnancy losses. So it's inferring an effect on pregnancy losses via the effects on this LBIC metric. Right? So you're sort of looking at the mirror image of pregnancy losses down there at the bottom. So there are some analytic considerations to consider when we're doing this. So the first one is this is by necessity something that's done at the group level. So any individual birth is uninformative in this kind of analysis. So you have to group people and exposures somehow. The exposures have to be relatively acute, so you can assign them to the pregnancy period. You can't use something like socioeconomic status, which is kind of constant across the whole thing. And very importantly, if you find an association with an exposure at some point during gestation, it does not necessarily mean that the loss happened at that point, right? So if you find an association with some exposure here in gestation, given the methods I've just described to you, the loss could actually occur at any point after that. All right, so that's just an intriguing little aspect of this. So here I was thinking, wow, I just developed this entirely new method. I'm so excited. I'm going to scream it from the rooftops. And as always happens in the world of science, you then soon discover that somebody did this before you. And that's what we discovered as we were writing things up. And I presaged that too soon, because this is not that slide. Let me give you this one first. So, right, things that affect conception should not confound an association with post-conception exposures, right? Unless they're correlated. And then you need to find a way to adjust for them. So if somehow a pre-conception exposure is correlated with your post-conception one that might affect conceptions, we have to deal with that. For air pollution, one of the key ones we have to worry about, especially for air pollution or other things, is seasonal trends. So there are seasonal trends in air pollution, and there are seasonal trends in conceptions, right? So that could lead to high exposure during pregnancy being somehow correlated with a conception pattern several months earlier. But the way we do this, and it's very typical in air pollution studies, is to account for seasonal trends with a spline term and take out effects of season on your exposure association relation. Singular events could also potentially confound. One way to get around that might be to look at, if you're looking at 1 year, you could look at the year before and the year after, when during the exact same time periods of the year, when the singular event didn't happen. So you've got the same seasonal pattern in the other years. You just don't have that singular event. That kind of a thing could happen. And some variations on standard analysis approaches are going to be needed, which I'll tell you in a moment. But now to the part about, yes, I thought I invented this whole new thing, and then I discovered that actually somebody used it before. As far as I can tell, this is the only time this kind of approach had been done, where Dean et al. Looked at the effects of a mass shooting in Tasmania, Australia, and looked at, although they didn't quite describe it the same way, what they were effectively doing was looking at these live birth identified conceptions and found that if that mass shooting had occurred when the woman was in the first trimester of pregnancy, there was almost a 30% loss in kind of expected births from those women. So had been done before in a slightly similar way. But not with air pollution. So what about air pollution? Can we look at that, right? How do we do this? Well, now we can actually do this with our data in hand. And because this was sort of new to us and we were worried, well, are we making some kind of mistakes, we wanted to do it in two places. So I added data from Boston. We took all birth data from the Beth Israel Hospital in Boston, and I'll show you in the next slide what years that is. For the exposure, we then could take 5 monitors around the Boston metropolitan area, and we just averaged them. Again, this has to be done at the group level, so we're not looking at individual mothers' exposures. We're looking at the Boston area exposure from week to week. We do the same thing with the models I described to you in the Tel Aviv district, week to week, looking at there it was not the 5 different monitors, it was actually their model of these things at individual 500 by 500 grids, but we just sort of averaged over them all for the Tel Aviv district for different weeks. So we're looking at how the whole district shifts up and down, data from temperature as a potential confounder from Israeli Meteorological Service, similar from Boston. As I said, the outcome data we actually took actual birth data from Beth Israel, did that resorting process I showed you to get week by week live birth identified conceptions between 2000 and 2013 at the Beth Israel in Boston, between 2010 and 2013 in Tel Aviv. In Tel Aviv, we took all births of women in the whole Tel Aviv district area. In Boston, we had only the births at the Beth Israel Hospital. Because our exposure measures were not quite as refined as in Tel Aviv, we first took them they had to live within 60 kilometers of Beth Israel, and then we did a subset who lived within 20 kilometers of Beth Israel. But an important thing that I'll get to now is what you'll see is in Tel Aviv we had many fewer years of continuous data, but we had many more births. In Boston we had many more years, many fewer births, and you'll see that from a power perspective, it's actually the births that matter more than the years. So what we're now doing with these live birth identified conceptions is the same kind of distributed lag model to say, does week-to-week fluctuation in exposures in Boston or Tel Aviv relate to the live birth identified conceptions that occur? We can look at week-to-week, so get those critical windows of exposure. We use natural splines. I won't go into the whole detail for these lags. We can include terms for seasonality that are also a spline to take out seasonal variation in exposure, things of that sort. We can put in indicators for holiday periods because holiday periods change conception rates, and if they happen to fall at a time of year when high exposures come a month later, that's a problem, so you can throw in indicators like that. And then what we do is, this is what I just showed you before, this is now actual Boston data from Beth Israel. So you'll see it's rather sparse. We only had about 80 to 90 births per week at the Beth Israel, but we resort them into our conception week. And now when we have live birth identified conceptions week to week, we line that up with our Boston area traffic pollution exposures week to week. And we simply ask the standard epi question, does this go up and down in concert with any of this? Okay? And we're doing that with a distributed lag, so we're accounting for all of these weeks at a time. This is the average data. You can see in Boston, the average number of live birth identified conceptions per week was only about 90, whereas in Tel Aviv it was almost 500, so many more births in Tel Aviv. Other than that, this is what I showed you before, that the actual NO2 exposure level is reasonably similar. So the mean 18, here it's 17, very close. You do get, temperature-wise, it's very different, obviously. Tel Aviv is quite hotter than Boston, so you can account for that. So the exposure is reasonably similar. This is the median distance from Beth Israel is about 12 kilometers for the women in this, in the full analysis, the 60 kilometers. They have to be within 60 kilometers. And this is what we see. So this is the estimated last menstrual period. So these are now the weeks of gestation. This is the distributed lag applied to the week-to-week fluctuation in live birth identified conceptions. The solid line is Boston, and I think this is the confidence limit for Boston. The dashed line is Tel Aviv, with this being, or maybe it's this and this. I think that's what it is. That's Boston confidence limits. This is Tel Aviv confidence limits. So we get a peak in the two, both right around weeks 15 or 16. Similar relative risks of dips in live birth identified conceptions. Again, remember, would be the equal and opposite effect on pregnancy losses. If we restrict to women who live within 20 kilometers of Beth Israel to try and hopefully get slightly better estimation of their exposures because they're not as far away, it actually looks even more similar, although the confidence limits get wider because we have many fewer in that analysis. Sorry, that offset there. But the bottom line is we're seeing sort of a peak of loss around, 15th week of pregnancy or so. So we are kind of excited about this whole approach. This is now in press, Kimurtzoglu et al. In Epidemiology. It's sort of this novel study design. It allows us to kind of comprehensively look at, right? So the sort of oddity but beauty of this is we're actually looking at pregnancy losses whether or not anyone even knew they happened, right? So that's the trick about this. We can use data just on live births. We don't have to rely on the identified ones in the medical data. We get the strong, very, very similar results in Tel Aviv and Boston, despite obvious differences between the two places. Strongest estimates right around 15th week or so. Again, doesn't necessarily mean the loss occurred there. And, this could start some process and the loss happens later. So, but the bottom line from this is that we feel we're finding actually a significant effect of traffic pollution on pregnancy, in early pregnancy, on pregnancy loss. So now, if that's the case, we have sort of said, yes, these two biases we're worried about can in theory happen if we do have this association between NO2 and pregnancy loss. The next steps for this new approach, we can talk about issues with it. There are some things we need to be sure we're getting right. So what we're trying to do is simulate a lot of this, just create simulated data and see whether we get what we might expect. So we're doing that just on the basic approach, like, okay, let's simulate data that has a seasonal trend in total conceptions. When we put in a spline, does it actually take that out? And that part we've done, and if you simulate a whole bunch of births and conceptions and estimated pregnancy losses, and you superimpose a seasonal trend in conceptions, you absolutely see this kind of association with traffic pollution. 5 minutes, okay. With traffic pollution, that is totally spurious because it's the correlation over time. When we put in a spline to account for seasonal trends, that goes away entirely. We're now trying to introduce effects of the pollution in our simulated data and see, do we get the same results we get? So we're doing that kind of a thing. And assuming that all works well, then the next step, of course, is to see, all right, if we know that effect, could it be accounting for that weird protection in autism we see? Again, in simulated data, because we don't know all this. And then to try and apply it, if we're comfortable with all this, in other settings. So overall, conclusions from all of this, right? the main thing about autism is we do see this decreased risk associated with early NO2 exposure, and we think that this is related to pregnancy loss. That's inducing these live birth biases because we can't analyze the ones we've lost, and that's creating this odd thing, which has important implications, especially since we do see an increased risk, at least in our data, slightly postnatally. Now, what does that mean for late pregnancy or really early post-pregnancy? That's a really tricky question because we could be mixing these two effects, which could be why we don't see anything. Or there could be an issue with the fact that, not every kid goes to 38 weeks. And so are we introducing weirdnesses because in that late pregnancy, early postnatal period, some kids have been born, some kids haven't been born. So that stuff to still work out. We do now see more evidence for this being driven by the boys, which I think is interesting. And now, sort of when considering those prior studies, we have to pay very close attention to, were different exposure windows being accounted for? How were they being handled? Could we be seeing strange things because of correlations or because of biased effects in one setting, in one window, and real effects in another, canceling out, things of that sort. And then there's this implication, which is really interesting, is that if this is happening and true, we now need to really understand the dose response of how an exposure like traffic pollution affects pregnancy loss. What is that dose response? And what is the dose response for an association between the traffic pollution and autism? Because depending on where those sit, you can get really yet another meta-paradoxical problem, which is that as you go to really high exposures, you may actually see less autism because you're losing more pregnancies, which leads to the weird scenario that as you do public health measures to bring the pollution down, you might actually start unmasking more autism cases because more of those pregnancies are making it to term. That's theoretical, but it's theoretical. It could be happening. So this comes to me because people always say, well, why are there not just children with autism all over the streets in Beijing or in Delhi? Well, there are many possible reasons, but one of them could be that such high exposures are creating such selection bias that you actually don't see as much of an effect of the pollutant exposure. There are other reasons too, so that's not the only one, but that's a sort of funny paradoxical one that always gets me excited. So with that, I just want to thank the people who really helped with all this work. Most importantly, Ron Raz, who's now at Hebrew University in Jerusalem, and Mariatti Anakiumortzoglu, I worked years to be able to pronounce that, who's now at Columbia, and Andrew Wilson, who's now at Colorado State. Our collaborators at the Technion, my whole group here, and then of course our funders, NIH, and some private funding. Thank you.
You asked for DT, you did not disappoint. So we only have 5 minutes. I was going to go to streaming, but I think we'll go to the room here first, if that's okay.
Yeah.
Hi, I'm Peter Carroll. I'm an atmospheric chemist, so a lot of this was very new and fascinating to me. But I would be remiss if I didn't point out that possibly one of the largest sources of bias is the use of NO2 as a traffic tracer. NO2 is not typically directly emitted from the atmosphere. It's also photosensitive, so during daylight hours it actually breaks apart. So it's not a great conservative tracer for traffic exposure. It also, in looking at the data you showed, could explain why, with similar NO2 levels, Tel Aviv had the lower risk ratio. Because Tel Aviv is 10 degrees lower latitude than Boston, which means it gets more sunlight, which means there's more photochemical reactions, reducing the NO2 levels. So while the measured NO2 was similar, the traffic exposure was actually probably higher.
Yeah, because it quenched it. So absolutely, so those are very important considerations to take into account. From the epicausal method side, what that effectively does is it creates a mismeasurement of what some theoretical true exposure, whether it's NO2 or another traffic thing is, and what we're getting out of our model, right? So you're pointing out that sunlight and the latitude may affect that NO2 measured level that we get. To introduce the kind of bias that creates an association in the exposure health outcome, those things would have to be related to the outcome in some way. So it's not impossible that it's not, and temperature is one thing that people have looked at with respect to birth outcomes, for example, and that's one reason we adjust for the temperature. But so what you're pointing out is absolutely true about measured NO2 and what it's actually telling you about what someone might have gotten out of a tailpipe of a car next to a street. But to take it the next step to, did it introduce an association with either the pregnancy loss or the autism, you have to then make the argument that those other factors that are driving that NO2 level in the atmosphere have to be related to the outcome. Right.
This isn't my field, but I follow what you're saying. I'm saying that the NO2 is a correlate for traffic exposure.
Yeah.
But in different areas and certainly in different seasons, the magnitude of that traffic exposure to the NO2 exposure are going to vary. And in places geographically separate like Tel Aviv and Boston, just basic fundamentals of the Earth's sunlight hitting Tel Aviv more during the day than Boston is going to lower those levels artificially. They're still going to correlate in all cases with traffic exposures.
Right.
But comparing on the same scale, Boston and Tel Aviv is masking that.
I see. Yeah. So it may be that overlap, the sort of similarity of results in Boston and Tel Aviv may not really be as similar as we think because of.
There might
So
be more exposure
yeah.
to each
So
other.
that could certainly be right. That could absolutely happen.
Can you comment on effect sizes in your study?
In which study?
In the postnatal group
Yeah.
that you had the effect?
Right. So this is important, so I showed two results. One is when we averaged over 9 months, and there, when we actually accounted for the pregnancy period and the pre-pregnancy period, we were seeing an odds ratio of around 1.3 or 4, I think, something like that. When you look at the DLM, when we went week by week, they were much smaller, right? So they were, I think, certainly below 0.1, I forget what it was. But that's because what you're looking at there is the independent effect of each week's exposure. So one, that is certainly much smaller. If we don't think the effect on autism is actually defined by a particular week of exposure, and that it could be several, you're going to see a much smaller effect size there. You're also, in both of those analyses, potentially seeing a reduced effect size of both of them from some reality because of the kind of mismeasurement issues you were talking about and others about how well our model reflects whatever the true exposure is. So in the 9-month average of 1.4, I mean, Heather can speak to this, that's actually in the range of what others see when they do that. So it's
Like right in the middle.
right in the middle of sort of typical odds ratios.
So we're at time. We are going to continue to take questions. I just want to say that if you do have to go, you don't have to feel guilty about sneaking out. But we will continue to take questions because we've got some folks on the schedule today.
So
Yeah.
neither of these are methodologic questions, they're just observation questions.
Okay.
So the first is, when you did the LBIC kind of analyses, which are super cool, did you see differences in those correlations between LBIC and NO2 levels by sex? Further arguing this question about...
That's a really good point. So we did not actually look at that, but we want to look at that and other things that might affect it. But intriguingly, no, wait a minute. I think we did, and in fact, we didn't see much difference there. Now, that doesn't mean it can't account for our autism effects because that U thing could somehow be different by sex, too. So,
Yeah, but it would, if you had seen it, it would
yeah,
make
then that
sense.
could be one of the contributors to, right. As I recall, I think Marianne did split it. My sense is she did, and it actually didn't look all that different by sex. Yeah.
And then my other question to that is, what about negative control exposure analysis for that?
So effectively it's in there if you believe that it looked like it came back down to 0 at the estimated last menstrual period. So if that is real, and honestly, we're doing a lot of simulations to see what needs to be the underlying effect sizes and things to see what you're seeing. And if you have effects very early in pregnancy, then it shouldn't come back to 0.
Okay.
But to the extent you believe that, or actually we could have gone we can't totally go preconception because if there are actually effects on conception, then that becomes problematic. But yeah.
Get you in 1 second. And just since you mentioned the U thing, because I'm worried about that.
Yeah.
So what are the candidate U's, sir?
Yeah, I mean, so I think, certainly genetics is a big one, right? That there may be genetic contributors to, they have to be things that are both related to fetal survival, and autism. But honestly, things like maternal stress of different sorts. I mean, certainly in animal models, stress is a huge predictor of loss in pregnancies. There's, as you know, there's some evidence that it may be related to autism. It could be other environmental exposures, right? I mean, this is an issue. We study air pollution. I think one of the reasons there's the most work on air pollution is because of the various advantages we get in how we assign exposures. And that I by no means think it is only air pollution. I think these other things are doing it too. They're harder issues to measure that and avoid biases and all that. But the U could be all those other chemical exposures that are doing the same thing.
The one thing about the genetics, at one point when I was thinking about this and I started to look at the genetics of fetal loss, I thought there was going to be this vast literature. And there's not. It's pretty thin, at least when I last looked.
I mean, frankly, like chromosomal abnormalities. Definitely one.
Yeah. That's true.
Okay, so he actually took one of my questions. But my other question dealt with other potential exposures for the moms early on in pregnancy and how that might contribute to or fend off early pregnancy loss. So how does prenatal care, early exposure to prenatal care, factor into what you focus on?
Right. So it's a good question, and one of the interesting things about this sort of newer approach I was talking about for looking at pregnancy loss is it's tricky in terms of what exposures we can look at because they have to be able to be assigned on this group level and blah, blah, blah. And we can't look at things like socioeconomic status this way because they're not time invariant. But we can look at how something like that modifies the effect of air pollution. So you could actually look at whether prenatal care and the level of prenatal care changes the relation between the environmental exposure, the air pollution, and the outcome. So that you could do. No one's done it yet, but you certainly could postulate that that would somehow buffer. Yeah.
We'll go there and we'll go there. Go right ahead.
Okay, I have a question. Please speak to my observation. In the past several decades, the standalone diagnosis of retardation has declined in the same proportion that the diagnosis of autism has increased because of mainly political correctness. Is this just a different form of retardation that people miss?
So I'm probably even in this room better people to answer that than me, but so I don't know the full literature on this, but my understanding or sort of my view of it, and others can certainly correct me if you think it's not right, is that while what you're saying is certainly a possibility, that there's definitely argument about exactly whether it really exactly balances out the changes, that certainly some of that sort of diagnostic switching could be accounting for some of the rise, but whether it's actually accounting for all of it is a open question. So I would say that in the context of sort of environmental exposures potentially affecting the risk of autism, that could be happening even if autism rates have in fact been flat for the last 40 years, right? So while if we knew that the rise in autism was absolutely biological, that would be a strong argument that the environment is contributing. I don't think it's a requirement that the environment is playing some role. And from my perspective, I think this rise that we see everywhere, we see it in Israel too. Certainly in Israel, some of our data would suggest that some of what you're saying, as well as other things like just awareness and interest in accessing government services, are playing some role in the rise because we see the rise in Israel at different time periods for the ultra-Orthodox, the Israeli Arabs, and the general Jewish population. So I certainly think that some of what you're talking about is probably contributing to some of the rise. Whether it's all of it, I'm not going to bet my farm on anything. But what I would say is that I think doing a sort of rigorous environmental epi study is probably the best way to get at whether the environment is contributing, and it could be doing that independent of the overall pattern and rise, whether it's happening or not, truly biologically happening or not in a population.
I have two unrelated questions. The first one is, if I understood correctly, that you were pinpointing a period of maybe 10 to 15 weeks. The losses that happen after the first trimester should be a lot easier to capture in medical records. It's mostly the very, very early losses where nobody knows how many there are, right?
Yes, yes.
So
Yeah,
when you're working with one hospital,
right.
can you capture
Yeah.
how many folks started with some prenatal care at their local OBGYN and then had a loss somewhere after that 10th week?
Yeah, so you're getting right at the crux of some of the issues we're trying to deal with in the simulation. So one of them is, I was originally thinking that we could actually do that, assuming that the later ones in pregnancy are probably all going to be caught. Could we apply this method to that and see whether it matches up? The issue there is there's some problems in that you're sort of conditioning on surviving until that, whatever, if you want to say take pregnancies that go to week 20, then now you're conditioning on surviving until week 20. So I originally thought, perfect, let's do that, and then now on the spot, I'm not going to be able to recreate why I thought actually that's problematic and I can't do it. It is certainly, so my thought was we do it both ways and see if we get the same answer. If we actually can't count them all, let's do the typical analysis and let's do ours. But I'm not actually sure that can be done.
So was it not a definite window? It was an example that it could be in that 10 to 15 week.
You mean where we see that sort of
Right.
peak effect? No, I mean, so that is where the DLM seems to be saying we're seeing the biggest effect. The issue with the DLM, and this is why we're simulating things, is that part of what it does is it kind of constrains the effect estimates you see from week to week. So it says, yeah, let's estimate them all, but you can't just go from 0 one week to 100 the next week to 40 to minus whatever, right? You've got to be somewhat constrained. So that, we play with how much constraint there is, and it seemed to be pretty robust in that. But what that may mean in practice is that if you have a very strong effect earlier, like at 6 weeks or something, or 8 weeks, and then not quite as strong effect later, the DLM could be kind of averaging, kind of misshooting both of them and kind of going in between. So actually it's trying to pick up a big early effect and a late one, and it doesn't have the flexibility to go whoop like this, so it kind of goes, okay, well, I'll do this to you. So that's what we're playing with now with the simulations, because it is true that once you get to week 20 in pregnancy, number one, most losses are probably identified. Number two, there aren't a lot. So to account for what we're seeing might be problematic. So we're now playing with, is it a huge effect early that is doing something weird to the DLM? So those are some of the simulation questions we're trying to ask. But I still need to think about more, because if I vaguely think that there's a way to take the sort of later identified losses and try and do the same approaches to both. So I'm still trying to think about that.
And my other question was about the sex differences that you brought up early on. We've been thinking a lot in our group about sex differences, because one thing that we're seeing is that there may be some differences in the trajectories of early identified girls with autism.
Yeah.
And so this would be much later than where you're looking at, who makes it to a live birth. But because you found the protective effect for the pregnancy values only for the boys and not for the girls, does that suggest that there's a different, I'm not even sure how to phrase it, but there's something there about the sex differences that's really intriguing to me.
Yeah, so it does, it sort of either suggests that you have a different effect of the exposure on pregnancy losses Danny was referring to, which we don't think we see, or it suggests that those sets of U's are different and acting differently in girls and boys, or it's the effect actually of NO2, although actually to see no effect in girls or a positive effect, you would have to then assume a much stronger NO2 effect in girls that would be balanced by the pregnancy loss. So I'm guessing that's not what's going on.
But it gets tangled up in how many girls with autism compared to how many boys.
Yeah, no, it
There's
gets...
something that happens before the births to girls, which is why there's so many fewer of them.
Yeah, well, right. I mean, and it could, and when, I guess the way I'm hearing what you're saying, it could be that you actually have different sort of mechanisms that get you to autism, right? And the phenotype, it might be a slightly different thing, right? And so then those predictors would be different in the two sexes, and so not create that same pattern. Now, all that said, with that, because there are many fewer girls, it may be that we actually are not quite powered enough to see the same nice pattern in boys, because some people don't see that in smaller subsets even with boys, this sort of protection thing. So it's possible that when the numbers are smaller, you don't see it as well.
Our time is over. James, is there anybody online with a
We
present?
haven't gotten any
Okay.
online
All right,
questions.
so with that, I will then extend our thanks and gratitude to Mark one more time for that.
Thank you.
I see making too much more money. Should have asked somebody like a national toxicology program.